Right, to start out with today's lesson, what I would like you to do is I'd like you to write down the following questions. Convert minus 18 into binary. So what you should be doing is you need to be getting the positive binary, flip it, add 1 to it, and that will pretty much give you the minus 18, okay? Now flipping it and adding 1 is a two-step thing, and that's a cue to remember that it is a 2's complement method you're using there. Calculate 19 and 35, you simply put down the binary numbers. It's not a negative, so you don't need to complement. You literally add them together, okay? So when you're adding, you need to do 1, 2, and 3. So it'll be 0, 1, 1, 0, and 1, 1 to help you. The more variable challenge will be to calculate minus 14 plus 26. So minus 14, you'll be using the 2's complement, which is the flip and add method to find minus 14 from the positive 14 binary. And then you're going to add that minus 14 value to 26 in binary to get the work in, to get the answer. And finally, you need to do an arithmetic shift left to the following binary places. Okay, so if you're doing an arithmetic shift left, remember that it's not logical, it's different to logical, it's arithmetic. And if you're doing a left shift left, you're doing multiplication. Just remember what the most significant figure is meant to do and what the end value is supposed to do. Two places mean it's going to go 1, 2. So can you complete this in your book for me, please, and we'll go through the answer for the next lesson. Now, I would like you to write down the title, 3 objectives, and the SMC question as neatly as you can. Remember that you're using a pencil and a ruler. Make sure you have that neatly as possible. Again, it's a pencil and a ruler. For the title and date, make sure you have this as neatly as possible. I will be checking your books. Now, this is what I'd like you to do. I want to talk you through hexadecimal, okay? We're going to remember what hexadecimals are and what binary is. Now, binary is 0 to 1, which is base 2. Denary is 0 to 9, which is base 10. That's our normal number system. Hexadecimal is base 16, so it starts at 0 and it ends in F, and there are 16 digits in it. So how does this look as a number system? Let's have a look. Before you do that, what I would like you to do is, I would like you to draw this hexadecimal table out in your book as neatly as you can. You will need this hexadecimal table to help you with the next sum. So can you draw this out neatly as you can with a pencil and a ruler, please? Now this is what I'd like you to do. I'm going to teach you how to convert from denary to hexadecimal, and then I'm going to teach you how to convert from hexadecimal to denary. So this is a hexadecimal. So let me see if I can work this out. Now we have 1, 2, so we have 1, 2, 4, we have 8, we have 16, we have 32, okay, we have 64, we have 128, okay. Now we know for a fact that we have an 8-bit binary. The first thing you need to do is you need to break this 8-bit binary into 2 4-bits, okay? Now this is a programmer joke and you might find it a bit funny, okay? I certainly do. So this is 1 bit. This is an 8-bit make 1 byte, and 4 bits, okay, so half a byte, which is 4 bits, you call it a nibble, N-I-B-B-L-E, okay? It's not a body part, it's a nibble. So you need to split it into 2 nibbles if you are getting a binary number. Now, first thing you need to do is, when you're doing this, you need to make sure that this is not going to be that, it's going to be the same, so it's going to be 1, 2, 4, and 8. We are converting this into 2 nibbles, so we treat it like 2 separate nibbles, okay? So you have 1, 2, 3, 4, 8, 1, 2, and 4, 8. Now, 2 and 1 is down, so we know for a fact that that's a 3, okay? 8 plus 4, 8, 9, 10, 11, 12, 13, 14, so we know that is a 14 in denary. Now, if you look on the hexadecimal table, we have 3, which is denary, okay, which is going to be 3 in hexadecimal. So the hexadecimal will be 3, and then 14 in denary is going to be an E, okay, so we know for a fact the hexadecimal number for this binary value will be 3E, okay. So 3E is your current answer. That's how you do it in hexadecimal. So this is denary to hexadecimal. Now the next bit I'm going to show you is how to get from hexadecimal back to denary. Again, we have numbers. Now we're going to split it into 2 nibbles, okay? Now D in hexadecimal is going to be 13. So I'm going to write down 13. 5 in hexadecimal is going to be 5 in denary. Now we're going to split this into 2 nibbles. So we have 1, 2, 4, 8. Okay. Same here. 1, 2, 4, and 8. Okay. Now as you can see, to make 13, I need 8, 9, 10, 11, 12, 13. So it'll be 1, 1, 0, and then 1. And then to make 5, you do 4 and 5, and the other two will be 0. Okay. So the binary value of this will be 1, 1, 0, 1, 0, 1, 0, 1. That's the binary value of D5. So that would be hexadecimal to denary. Now, this is what I'd like you to do. This is a question. This is actually a really difficult question. If you can get this question and you break this, you're 100% confident you can do this, okay? So graphic designer uses the website to publish their photographs. They wish to use a specific background with the hexadecimal color code. Now, some of you might recognize colors being coded like this, and that's the color code given. Convert the background hexadecimal into binary. Now, as you can see, we have a lot of different ones in there. So let's have a look how we can break this down. F is going to be a nibble by itself. 2 is going to be a nibble by itself. 23 doesn't because it only goes up to 16, remember. 3 is a nibble by itself. 7 is a nibble by itself. And A will be nibble by itself, and then B will be nibble by itself. Can you take it all away using the hexadecimal table, and can you find out what the binary equivalent is to all of them, please? Now F will be 15, okay? So in fact, F, 2, 3, 7, A, and B, okay? So 1 mark for 24-bit response, okay? 1 mark for all correct answer. Now that we've talked through that, what I would like you to do is, this is actually that much in denary, by the way. Now, I would like you to get your workbook out. I'd like you to go on to page 36 and complete everything in page 36, all of the questions, okay, and actually get you to master that topic. And then I would like you to have it go at page 110 for me, please. Now, at page 110, if you flip to there, you would actually get the answers for page 36. Just self-assess at the end of the lesson disciplinary. Try not to copy it because you, as a group, 10A1, you guys are much sharper than that, okay? So have a go at that for me, please. Now, this is the last question of the day. Benefit of hexadecimal. Why do programmers prefer to use hexadecimal notation to binary? You might be thinking, why do I need to know base 16, okay? Now, computers understand binary really well. Human beings understand denary really well, okay? Because that's because we have 10 fingers. We've always used decimal 10. Now, that is because instead of writing a 8-bit number, I can reduce. So for example, if you look at the example right here, instead of writing an 8-bit number, I can pretty much write a much smaller hexadecimal version instead of a massive binary. Besides, I'm never going to remember this number. I'm most likely to remember this, okay? Another example will be, I will most likely to remember this color code as opposed to this binary value. Besides, I might get the ones and zeros mixed up, okay? So the shorthand method is easy to write and easy for humans to read, and is likely to reduce errors, reducing the potential of mix-up. Can you write down this question and write down this answer as well, for me, please, for your future reference? And that, year 10s, is the end of the lesson.